Hello, and welcome to the virtual visual question answering and dialogue workshop. Today, I'd like to talk about learning to fill in the blanks in video and language. Let's start with an example. She ushers Minnie into the house, swigging from a bottle of blank. As humans, we can form various hypotheses as to what blank may be. It could be wine or beer or juice or some other beverage. However, this is a description of an actual visual scene, so looking into that scene allows us to answer that she's actually drinking cola. So this kind of task, multimodal fill-in-the-blank task, requires us to jointly reason about text and image or video, and language alone can give us an answer, at least most of the time. So we do this a lot actually when we do this masking, pre-training for multimodal BERT models. However, today I'd like to look into what can we actually learn from the fill-in-the-blank tasks and what sort of reasoning may be necessary to address them and how can we perform such complex reasoning. So let's dive in. What is happening in the video clip? I'd like to highlight several prior works, including our own. At the top row, there are examples of multiple choice tasks where the blank has to be selected among these few given choices. The bottom row, there is our prior work as well as an extended work where it's an open-ended fill-in-the-blank task. So there is a large number of possible answers. And also in this follow-up work, there are multiple blanks. So we limit this to a single word blank, and we look at nouns, verbs, adjectives, adverbs, covering a vocabulary of over 3,000 blanks, which is also a pretty long tail distribution over these blanks. So a typical pipeline could look something like this. We could have 2D or 3D CNN features over the video, also encoded with an LSTM. We could have a bidirectional LSTM over the question to capture the blank. This is what the typical methods looked like at the time of this work, that is about 2 years ago. What have we learned from running this challenge? So first we found that humans, leftmost column, do much better when they can see the video, rightmost column. So they clearly benefit from seeing the video. Then our initial architecture slightly improved over the text only, but the improvement was not large. And in the subsequent years, we see that the improvement has gotten bigger, but there is still a very large gap to human level performance. So the improvement has been largely possible due to better multimodal fusion techniques. One set of observations here is the top performers answer a large number of questions in the same way. That is, there is a significant language prior driving these predictions. Then many cases when the models are correct are sort of limited to this common vocabulary of frequent concepts, while they tend to fail over much more varied vocabulary, longer tailed of the distribution. And we also had humans evaluate these models, and their results agree well with our automatic evaluation. So where these models can do well is typical scenes like office, or typical actions like nodding. But then we see a failure case. Here is a slightly more difficult example where there is a stick that he is picking up, and the language bias finds to say walking away as a much more likely and confident guess in this case. So some of the takeaways: the movie fill in the blank is a task which requires understanding of text and video, which can be automatically evaluated. Language is important, but video really is necessary as shown by human performance. The models that we had about 2 years ago do fairly well on scenes and common actions, but then they overfit to language. They don't really exploit visual features as they should. So I think this opens interesting opportunities for improvement, to see whether we can use better visual features, develop better fusion techniques, and jointly reason about text and video, because some of these tasks can be fairly nuanced, where we really need to align the video and the sentence to understand the answer. So I think it's time to revisit this challenge with modern tools to see how far have we come in the last couple of years. With that, I'd like to move to the next challenge, that is, who is acting in the sequence of clips? So here we are looking at a story, at a sequence of descriptions. Let's consider this example. His brow furrowed, blank looks down at the ground. Blank eyes him angrily, her jaw clenched. Blank heads off. How do we predict the identities for these blanks? So we can hypothesize that, well, the first obviously is a male character, so let's just label this as person 1. And the second description corresponds to a female character, so naturally it's a different person, person 2. And we don't really know who the person 3 here may be. Is that person 1, person 2, or a third person? So we need vision to resolve this ambiguity, or we need more context. So let's continue and see what if we have more context. Blank folds her arms. So this corresponds to a female again, so we could guess that this is person 2 and make this connection. And looking at that, we may come up with a reasonable guess that that corresponds to person 1, who heads off. If you have another sentence, blank approaches blank, who leans against the wall of the house, then with all the prior information that we have seen, we could hypothesize that this is a person 1 who was heading off, and person 3 is somebody we haven't yet seen. So as you see, we have to rely on several assumptions and make some guesswork here if we don't see the video. So seeing the video, seeing the visual appearances of these people allows us to more robustly perform this task. So we require complex reasoning over a set of clips and sentences, and we still really need video to address this. So we have collected annotations for the LSMDC data where every named instance or he/she pronoun is now labeled with an ID. And we also have gender labels for these characters. And we focus on a local scenario, that is a short set of 5 clips, not a global setting where we want to tackle an entire movie. So we want to stick to this more general case of sort of locally identifying within these 5 clips. So what sort of distribution do we have over the person IDs in these local sets? As one would expect, there is few characters which unique, which would be mentioned in this time scope of 5 clips. So person 1, 2, 3, and 4 tend to dominate this, and then it's less likely that there will be person 5, 6, or more within that time frame. But this still poses interesting challenges as to how to correctly match these blanks, or when not to match. So how do we address this task? So on the left, I show a sequence of blanks which we want to ID. And our hypothesis here is that to really do this properly, to predict coherently the IDs for this entire set, we want to frame this as a sequence-to-sequence prediction problem. So we want to describe each blank with a local representation S, and then feed these representations into a transformer model, which would then exploit their mutual relations to come up with the labeling. So that is our high-level idea in this work. And then for more details, I will just give you a gist of how we get this blank to face linking. So we have facial clusters and other video features, and we perform attention mechanism over these facial clusters to basically match blanks to one or more clusters. And then these attended visual representations and the blank encoding together form our representation S, which we feed into the transformer. So how do we evaluate how well we are doing on this task? So we choose the following strategy. We want to compute a pairwise accuracy. So we look at all pairs among the ground truths and the predictions. And for every pair, we can say if they are the same ID or a different ID. So a link or not a link. And then we compare these sort of matches for the ground truth and for our prediction and come up with an accuracy that is 4 out of 6 here. We have they are in agreement with each other, and 2 times this agreement is violated. So this resembles the precision recall as defined in clustering, sometimes a sort of pairwise precision recall. However, we have to use accuracy in this case because we are dealing with a special case with singleton clusters possible, so we cannot always rely on precision and recall in this case. Let's see what performance we can get if we just try 2 naive approaches. So same ID that is always predicting person 1 and different IDs that's predicting a sequence of 1, 2, 3, 4, 5, etc. So these are the numbers, and not surprisingly, they sum to 100 because they simply reveal how many times in our data set the pairs are the same ID, that is about 40%, and about 60% of the time it's a different ID. So this is just sort of illustrating what types of tasks exist within this data. The 40% of the time we have to link, and in the remaining cases we need to not link the IDs in a pair. Now our text-only model, that is the same architecture but without any visual features, does fairly well, and with additional visual features we get a small boost. And we compare to state-of-the-art from last year, the challenge participants, and we see that we can outperform both of those methods. Both of those methods actually rely on sort of local decisions about pairs of blanks, whether they are a match or not, which is different from our method, which is, like I said, addressing this in a more holistic manner as a sequence-to-sequence problem. Now, human who does not see video does better than all of these methods. And now if we zoom out, we kind of see that, well, humans who can see video does even better. So there is indeed a large room for improvement here. We analyzed the difference in behavior for our method and these 2 concurrent works, and we see that our method can much closely capture the distribution over these IDs that exist in the ground truths, while these 2 methods tend to underlink this frequent person 1 and overpredict other diverse IDs than necessary. Here is an example. So we have ours correctly identifying person 1 in 2 first clips, and then person 2, then person 1, and then both of them are seen in the last clip. The Yu et al. Misrecognize this as person 3, so they label this differently, and then they correctly link her to her appearance in the following, but they basically miss to re-identify this person And then they recognize in the last clip these guys as totally new characters. And the same mistake is done in the other method. If we want to gain some more insight as to what vision gives us as opposed to text-only model, here's an example. We have some ambiguous case here where blank and blank join blank. In ground truth, this is a male and female and a male. And at first, both models sort of get this wrong and just predict everybody as male, which is a more frequent gender in this data set. However, the visual model then recovers and says that person 3 is actually a female, and then consistently links her to her appearance in the following clip with the right gender, while the text-only model fails to identify the gender or to link these characters at all. So one interesting feature or use case for this fill-in-the-blank task is that it allows us to perform identity-aware video description. So conventional description models gives us these someone looks at someone type of descriptions, while now we can go and basically relabel all these someone predictions with IDs and get much richer and much more informative story out of this. So to summarize this part, the fill-in-the-characters task allows automatic evaluation based on this pairwise accuracy. And the initial results are encouraging, but there is a really large room for improvement. So I believe some of the open issues and which offer basically room for creativity here is how do we incorporate more spatially and temporally localized, sort of grounded visual representations that would overcome some of the challenges where we sort of where the ambiguity is to see which character the description is actually referring to, as there are multiple people in the scene. So how to more effectively use the visual modality to see more significant gains over the language-only model. And also, like I showed you, we as humans can perform all this pretty complex reasoning step by step. Can these models do this? And how do we teach them to do this? So this brings me to the last part of my talk, how to perform complex reasoning. And here, this is not applied to the video understanding yet, but I think this opens an interesting opportunity to look into it. So here we are concerned with the task of relational reasoning. And first we posit that reasoning with local features is hard. So what I mean by that is, let's contrast two scenarios. First we have a question, is there a woman in the image? And we can find this region which has woman in it and answer yes. And so local feature is enough to basically give us that answer. However, the question is the woman sitting on a chair? No single local feature will give us an answer. We need to look at this woman, look at the chair, and understand whether the relationship is satisfied. So we want to contextualize our features, for example, a feature of a woman with respect to the chair, to answer this question. How do we contextualize, what sort of context should we build in? Well, the task itself, that is the question here, suggests us that this should be a language-driven contextualization. That is a woman in the chair, or in the second example, is the woman on the left of a man. Naturally, we want to consider man as a context in this case. So next, how do we effectively implement this? How do we actually model this context? For that, we want to use graph networks and propagate context from one node to another, where each node is a local feature, using message passing. So at a high level, this is what our language conditioned graph network look like. So we have considered several tasks where we have an input description, a question, and an image. And we have a set of these local features, which could be object-centric or not. So our goal is to transform these local features into these context-aware features, which we can then use in our downstream task-specific applications. So what happens here is the message passing mechanism, where at every step we attend to a textual command. And the textual command is sort of some part of the question that is relevant at a given time step. And with this textual command, we then consider what edges are important to really basically answer the question. Sort of we weigh the edges based on their importance. And then we send messages from one node to another, incorporating their local and contextualized representations. And then each node sort of aggregates all the messages and updates its own contextualized representation. And then finally, each node is then represented with the combination of local and contextualized features, which jointly form the context-aware feature. Then we can plug this into very simple VQA or grounding models. And in practice, experimentally, we found on 3 different scenarios in VQA and referring expression comprehension, this method to be really effective with very, very simple downstream models. And for details, please check out the paper. I just want to summarize that LCGN is a fairly general context-aware representation, and we show the importance of language conditioning in this message passing mechanism, and which allows also for the dynamic weights on the edges, which allow us to approach the visual scene differently each time when we have a different question given to us. So to sum up my talk today, I'd like to argue that overall we see less progress in video and language that we have seen in images and language. And there is a number of data sets and tasks out there. So I want to, of course, say that our tasks allow for straightforward automatic evaluation. That's a plus. So you can easily see progress. And we see that there are some interesting challenges here as to how to overcome the language-only baselines, how to bring in stronger spatial, temporal, localized visual representations, and hopefully this task should benefit from those. Also, we want to think of how do we jointly reason about text and video, video having spatial and temporal extent, as well as potentially other modalities like audio, and maybe bringing in dialogue, and sort of how all of these modalities jointly would allow us to bridge this gap to human performance. I think LCGN that I've briefly discussed and transformers naturally are promising directions, and I'd like to see people try these modern tools on these challenges. So please go ahead, check out our data sets, check out also the code for LCGN if you're interested, and I'll be happy to get questions during the live panel. So thank you for your attention, stay safe, and carry on doing cool stuff. Bye.